Hello everyone. So, hopefully you read my Canvas announcement. As I said there, I've made the decision to go ahead and move forward with video lectures for our class. So, the video today will be a test video mainly, and it's going to be mainly about material I've talked about on our last in-class meeting. That was last Monday. So if you're there that Monday, a lot of this material will be review, though I do want to say right now at the very end of the video I do include an example, and I talk about new material that we didn't get a chance to talk about on that class meeting. So at the very end, even for you people who were there that Monday, there is new material for you to check out. So please make sure you go and watch that. Besides that, as I said, we're going to be moving forward with these video lecture formats. I'm going to post these weekly on YouTube, on this channel. Hopefully this is where you found it. So with that in mind, since this will be the new format for our class, please make sure you give me as much feedback or comments as you can about this video, as these are for you guys. I'm trying to make this as best as possible as I can for you guys. So whatever feedback you can give me will be greatly appreciated and will help me improve this new system moving forward. Without further ado then, let's go ahead and get into this lecture. Alright, hello everybody. So today, what are we going to talk about? Well, if we will remember back to, I don't even know how long ago it was now, when we had our last in-person class, we talked about how to read functions, how to read the domain and range off of a function. So we're going to continue with that. This time around, we're going to talk about how to read increasing, decreasing, and constant intervals off of a graph, alright? And then in addition to that, we're going to talk about how to read relative max and mins off of a graph, okay? So this will be our end of our discussion of how to read graphs, and after that we're going to actually get into how do we actually make graphs, okay? And the biggest tool for us is going to be this idea of translations of graphs. And what we'll see is that there's two big categories of translations, two big bodies. There are rigid and there are non-rigid. So that's what we're going to spend our time talking about for this video. So let's go ahead and get on into it. Alright, so increasing, decreasing, and constants. I'm going to try to always keep this halfway mark. Alright, so increasing, decreasing, and constants. Alright, so what do we mean by that? Well, we say a function is increasing. Alright, so we say a function is increasing if as x moves to the right, the function value gets larger. So again, we say a function is increasing if as x moves to the right, the function value gets larger. Okay? Now conversely, there is decreasing. Alright, so we say a function is decreasing if as x moves to the right, the function value gets smaller. Alright, again, so we say a function is decreasing if as x moves to the right, the function value gets smaller. Alright? So quick visuals. Say we're moving along to the right on x. X is moving along to the right. Then our function value f of x is getting larger. Similarly over here, as we move along on the right on x, so as we're moving in the positive x direction, that function value is getting smaller. That that is decreasing. So that's increasing and decreasing. All right, pretty straightforward, very intuitive. We already I'm sure we all understand what it means to be increasing, what it means to be decreasing. So I'll give, all right, so here's a chance to pause the video and write these definitions down. Okay, so now let's move on to the last one, which is constants. So constants. And I'm sure you already have all guessed what it means to be constant. So we say we are constant a function is constant if the value of the function does not change. So we say a function is constant if the value of the function does not change as x moves to the right. Sure, let's keep it consistent. As x moves to the right. Okay, so then, another quick visual. We are moving along to the right, and that function value, let's say, doesn't change. It's a horizontal line. We are constant. Okay, so those are our three types of intervals. All right, let's actually keep note of that because I didn't really emphasize in these definitions, but these are intervals. So when we're solving problems, asking for when am I increasing, when am I decreasing, when am I constants, right? We're going to be talking about intervals, so our answers are going to be in interval notation, but we'll see that when we get to an example. Before we get to that example, there's one other topic I want to introduce. Oh, I forgot to give a moment to pause and copy, so find a moment where I was rambling where you could pause. But here is the last topic I want to introduce before we get into our example, and that is this idea of relative max and min. Let's talk about relative max and min now, okay? So what does it mean to be a relative max? A relative max is a point where before the point the function is increasing before the point the function is increasing and immediately after the point the function is decreasing. Okay, so just to recap, a relative maximum is a point, so we're talking about points here, is a point where before the point the function is increasing and after the point, immediately after the point, the function is decreasing. Alright, so what we're going to see here, and what's important to note, is that relative max and mins are classified by behavior. All about the behavior of the graph that gives us these relative max and mins. So for the maximums, it is an increase immediately followed by a decrease. Alright? So I'm sure you can all guess already what the relative minimum definition is. So here's your chance to pause and copy the definition. Alright. So I actually only need to erase select portions of this definition. So, a relative minimum is a point where before the point, the function is decreasing and immediately after the points, the function is increasing. So, as always, when we're introducing these types of pair definitions, one of them is analogous, or is the direct opposite of the other. So that's what we have here for minimums. It is a point again, but this time the behavior we're concerned about for this point is that it is a decrease immediately followed by an increase. That will be a relative minimum for us. Okay, so yet again, here's your chance to go ahead and pause and copy the definition. Okay, so now there's a point we actually have to talk about when we're talking about these relative max and mins. And again, just like increasing, decreasing, constant, we probably already have a good intuitive idea about this concept. But that intuition we have is actually going to come and bite us in the butt, basically, because we have to be very careful. There is a big idea, there's a big difference between these two ideas. Relative max and mins, absolutes. Max and mins. Alright, so there is actually two categories of maximums and minimums. There's relative and there's absolute. And for us in this class, we will only ever be talking about relative. We don't actually talk about absolutes in this class. So what do I mean by that? What is this difference between absolute and relative? Well, it's best seen visually. That's pretty much all this lecture is just visual explanations. So say we have some function like this. A, B, C, and D. We have some function like this, that's its graph, and it has these 4 points, A, B, C, and D, alright? So what are the relative max and mins of this graph? So, here's where our intuition, our common sense intuition kind of bites us in the butt, because our common sense intuition tells us that right there is the smallest point. That must be my minimum, alright? And yes, that is a minimum. That is in fact the absolute minimum. But we're not concerned about absolutes. We're trying to talk about relative. So when we're asking the question, what is the relative minimum? Again, we have to go back to that definition. And relative minimums are all about behavior. And the behavior for a relative minimum is that it must be decreasing before the point, and immediately after the point, it starts increasing. And that's what we see right here at C. Alright? Because before the point C, my function is going down. It is decreasing. Then we hit the point C, and immediately after that point C, the function starts going up again. It's increasing. So that right there is the exact behavior we're looking for. That satisfies this idea of being a relative minimum. Okay? And so conversely, with that, what is our relative max for this point? Well, again, right? D intuitively is the maximum. That is the largest point on this graph, but it is not our relative maximum. Because again, it does not show the behavior we're concerned about. It does not show an increase followed by a decrease. The point that shows that is B. Because here we are increasing, we hit B, and afterwards we start decreasing. So that is why B is our relative maximum. So just be very aware of this as we talk about and do problems like this for this class. There may be cases in which our maximum point and our minimum points aren't relative maximums and aren't relative minimums because they don't show the proper behavior. Alright, so take a moment for everyone to, I guess this will be our star, one of our stars for the day. So here's your moment to pause and copy this down. Okay, so then, let's go ahead and move on. And 1 second, make sure I'm not forgetting anything. Oh, and yes, okay. knew I was forgetting something. One last note before we move on to our first example is continuing with these max and mins. Our next star is that it is possible for a graph to have multiple relative, I guess that's worth actually writing the whole word for, relative max slash mins. Alright, so a graph does not need to have one relative maximum and one relative minimum. It is possible it can have 20 relative maximums and 15 relative minimums, and it may even have no relative maximums or no relative minimums. That is possible. Okay? So, that was the last note I wanted to make, so again, chance to pause. Beautiful. So let's do our first example now. It is very hard for me right now to not stop and ask, is everyone okay if I erase? That is, don't want to make a fool of myself. But let's continue. So, our first example. Okay? Our first example will be this. Let's identify the increasing, decreasing, and constant intervals and relative max and mins. Alright, so let's identify the increasing, decreasing, and constant intervals. In addition to that, let's also figure out what the relative max and mins are of this graph. And the graph we're going to do is this. Make sure I get plenty of room to sketch it. Give me just a moment, guys, to sketch this graph. Let's make that a bit. Okay, so here will be our graph. Okay, so let's go ahead and talk about this now. Let's figure out what our relative max and mins are. No, my bad. First, let's identify what our increasing, decreasing, and constant intervals are. So, how do we do that? How do we figure that out? First, let's just take a look at the graph. And visually, as I said at the beginning, it is not hard to get a sense of where is my graph increasing, right? As we just look at the graph, we need to ask ourselves basically, when does my graph get bigger? And one obvious answer is right here. Right there is a portion of my graph that is getting larger, okay? So the question is then, how do I express this as an answer? How do I write this as an answer? So that goes back to the comment I made in that we are talking about intervals. So our answers must be given interval notation. So the question is, now, what is the interval that expresses this portion of our graph? And so that basically means what are the x values that make up this portion of the graph? So that simply means we go to here and we simply have to translate back down into what our x region is. So if I start right here at the leftmost area, the leftmost portion of the graph, where does my graph start, in other words? It starts at that point. What is that point? Well, it is -7, 2. And again, we are concerned about x values. So that means I want that -7. That's where this interval, this portion of my graph starts. It starts at -7. Okay? Where does this interval end? Where does this portion of the graph end? Well, it's going to end at this point right here. Alright? What is that point? That point is 3, 5. So again, I want the x value, so I want the 3. So there are the two values that are going to make up my interval. Now, as always, when we're talking about intervals, we have two tools. We have parentheses and we have brackets. So we need to identify now, which tool do I want to use? In other words, do I want to include the points or do I want to exclude the points? Now, for me, actually, I will be happy if you use either parentheses or brackets as long as you stay consistent. And what I mean by that is, for me, I would write parentheses here. Alright, why is that? Well, I'm basically making the claim then that by using these parentheses, I am saying that we do not increase at -7 and we do not increase at 3, but we are increasing at all values between those. And to me that makes sense, because let's imagine here at this -7, that's where we start. So at -7 we are on the ground. It's like we're laying on the ground. Nothing's happening. We're just laying there. But right after -7 we start getting up. We start moving up and we start moving. So that's when things start happening. That's when we start increasing. But at that -7 we're flat. Nothing's happening. We're just laying down. That's why I say we do not increase at -7 and I don't include it. Alright? And conversely at 3 is this interesting point where we have to go, I guess kind of a physics side tangent. 3 is an interesting point because 3 is this, imagine this. I have my marker. I'm going to throw the marker into the air. That marker is going to go flying into the air, and eventually it's going to hit its highest point, right? So in other words, I throw my marker, and the marker goes flying through the air, goes up and up and up, and eventually it hits its highest point. And what's happening at that highest point? Well, here's where the physics comes into play. Well, to dumb it down a lot, what happens at the highest point is the velocity of the pen kind of dies out. Gravity's pushing down on it. It wants to bring it back down. And so there's this magical moment in the air where both the velocity or the acceleration pushing the pen up and the gravity pushing the pen down cancel each other out. And once those forces cancel each other out, there's the briefest amount of time you could possibly imagine where the pen just stops. And it literally floats in the air and it does nothing. It just floats there and it does nothing. And then just like that, before you can even imagine it, gravity takes hold and pushes the pen back down. But there is a moment at exactly that value 3 where you're just floating and nothing is happening. So in other words, it's not increasing, nor is it either decreasing, it's just there. So that's why I say we put another parenthesis at the 3. Yet again, I won't be mad if you stay consistent between your use of parentheses or bracket. And what do I mean by consistent is that if I put a bracket here, then there should be a bracket on 3 as well. Alright, something like this, where it's a mix of bracket and parenthesis, I would not like. Please make sure you just stay. If you want to use bracket or parenthesis, just make sure you're consistent. Okay, so beautiful. That is the interval of that region of the graph right there. Okay? Well, is that the only increasing interval is our next question, right? Because we only talked about this part of our graph. That's not the entire graph. So again, we go back to that intuitive sense. We just look at this graph and we say, well, is there anywhere else I'm going up? And yes, there is. There's actually 2 more places. The first one is right here. Alright? That is the next portion of our graph that is moving up. That is our second increasing interval. So, let me make sure I give myself enough room. I can have 7,3. Alright, now what is this interval? Again, we do the same game. Where does it start? Where does it end? Okay, so we start at this point right here. Alright, the point right there. Now, there's no labels on that point, so we have to ask us, what is it? Well, that's where we remember, that's the special point on our Cartesian plane. That is where both axes cross. It is our origin. It is the point 0, 0. So, right, an x value of 0 right there. That's where we start increasing. Alright? And we move up, 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 increasing, 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 until we hit that point. That's where we're going to stop increasing. So again, what is that point? It is, that should be a -3. -3. Okay, so that is the point, 3, 5. So we want the x value. We are 3. Beautiful. There's our second increasing portion. Alright, and lastly, we go through again. We have to make sure we go through the entire graph. Is there anywhere else we're increasing? Is there anywhere else we're going up? Yes, there is one more part right here. Beautiful. So let's go ahead and write that portion down. Again, we start with asking, where do we start on this increasing interval? We start at this point. Okay, great. What is that point exactly? That is the point 4, -3. So again, we take the x value of 4. Now, here is where it gets interesting, right? Because we're no longer using points, right? We have to ask ourselves, where does my graph end? When we were doing this interval, we said I started at this point, I ended at this point. Great. For this interval, though, I start here at this point. Wonderful. But do I have a point I end at? Well, not quite, right? Because I have this arrow here, right? What does that arrow mean? It means I'm just moving forward forever. I'm not stopping. So that's why in this class, we always have to remember, I guess here's a note, always have to remember is that arrows imply positive or negative infinity. All right? Arrows imply positive or negative infinity when we're talking about graphs. Now, which one is this one talking about? Well, this one's moving in the positive x, right? This is the positive x direction, so this would be our positive infinity. And there you go. There are the three increasing portions of our graph. Now, as always, we're not quite done. There's one last thing we need to do. We have these three separate intervals that each express the same graph. So I would like it so that this is one giant interval, right? How do we connect disjoint intervals? With our u, as always. So there you go. That right there is the increasing interval of this graph. This whole big thing right here. All right then. So with that out of the way, we can immediately move on into the decreasing. Oh, I guess let's not use blue. We can immediately find what our decreasing is just by doing the same game. All right. Visually, where are we decreasing? We're decreasing right here. Okay, that's visually where we're decreasing. What is that interval? Well, we start at this point. That point has a value of -3. Beautiful. We end at this point. That point has a value of 0 for x. Great. Then we go back into here. All right, that is our next decreasing. I know that graph is getting a bit cluttered, but I don't know. I think the color coordination helps. All right, so we get back to here. Where does this decreasing start? It starts at this point. What is that point? It is 3, 5. So I want that x value 3. Where does that point end? It ends right here at 4, -3. So I want that x value of 4. And of course, we connect these both with a u, and there you go. There's our decreasing interval. Wonderful. Now then, there's one last type of interval. That is our constant interval. We need our constant interval, okay? So for this one, we're going to look at our graph, and we're going to say, well, am I constant anywhere? And we can say, well, no, right? How can we know for certain? Well, I've circled every portion of my graph. There is nothing about my graph I haven't circled, so there's nowhere I have a constant interval, right? And as we saw in that quick visual example, constant intervals are going to be that horizontal line, and we don't see a horizontal line here. So for this graph, we simply don't have a constant interval. Wonderful. So now let's talk about the relative max and mins for this graph. So that's half of the problem we've just done. We still need to do the other half. That's identifying our relative max and minimums. So what I'm going to do right now is I'm going to erase this little arrow imply note. So if you don't have that written down, go ahead and do so now. Okay, so now let's identify the relative max and mins. So what is the relative max? So remember, we're talking about points now. What is the relative maximum points, or points, because we could have several. We just need to identify that. And remember, as I said, it's all about behavior. Behavior, behavior, behavior. What is a point on this graph? What is a point on this graph that is, before it we have an increasing interval, and immediately after it we have a decreasing interval? Okay? And as we should all hopefully be able to see, one such example is right here. At this point. That point is increasing up until the point, and right after the point we are decreasing. That is a relative maximum. So what is that point? That is the point -3, 5. And as I've already said though, it is possible for a graph to have multiple relative maximums. So just because we identified one doesn't mean we get to stop. We still need to make sure we read through our entire graph looking for any other points that satisfy our behavior. So let's just start from here and let's read along, all right? I'm decreasing, decreasing, decreasing. I hit a point. Okay. Let me start over. We're starting at this point. We're looking for increase followed by decrease, all right? So we're just decreasing all along here, not our interest. Right now we're looking for an increase. That's what we want to see. So none of this decrease interests us. Bam, we get to here. We're a increase. Okay, so now I should start paying attention. So I'm increasing all along here. And then eventually I get to here. And what happens right after I hit this point? I start decreasing again. So that's the exact type of behavior we're looking for. It is an increase, we hit a point, and after that point we start decreasing. That is the behavior of a relative maximum. So this point as well is also a relative maximum. And that is the point 3, 5. So we have 2 relative maximums. Beautiful. Alright, let's identify the relative minimums. We will have 2 for this graph as well, alright? Alright, so the relative minimums, okay? Well, all going back to behavior, yet again, we are looking for the behavior of a decrease. You hit the point immediately after you increase. And so there are going to be 2 relative minimums for this graph. They're going to be these points here and here, okay? Yet again, this point is that special point. It's where the axes cross. It is our origin. It is the point 0, 0. So why is it a relative minimum? Well, it's all about behavior. Before this point, along this region, we are doing nothing but decreasing. We are decreasing, decreasing, decreasing. We hit that point. What happens at the origin? Immediately after the origin, that value of the function starts going up again. It starts increasing. Decrease, point, increase. The origin is now relative minimum. By the exact same logic, this point right here, which is 4, -3, is also a relative minimum because you are decreasing. You hit the point and then you are increasing. So this as well is also a relative minimum. Okay? Beautiful. Now then, let's go ahead and move on to another example, shall we? So I'm going to go ahead and erase all this. Take a moment now to pause the video if you haven't copied all this down. Alright. So we're going to do another example, same directions. We will identify the increasing, decreasing, constant, and relative maximums. But the example we're going to do this time this example. So we're going -3, -1. Okay, so here will be the next graph we talk about, okay? So with this example, we're going to do a bit differently. I want you all to stop the video at this point, go ahead and do this problem on your own, alright? Then when you unpause this video, I'm going to blitz through this, okay? So really, take the time to think about this. So go ahead and pause the video now. Okay, so I'm going to go ahead and blitz through the answer, right? So please try to give this your honest effort when you're trying to identify all this stuff. So let's start with increasing. Our increasing interval, there's only one. It's right here. And that is 1, 1, 2. That's the only portion we're increasing. Decreasing. Decreasing, alright? We have 2 regions. We have this region and we have this region. Okay, so yet again we have an arrow here. We have an arrow, we are moving in the negative x direction, okay, that means this value, this interval starts at negative infinity. Alright, hope that all makes sense, right? You keep on following that arrow that way forever. You're asking yourself, what is the smallest x that makes? That'll make negative infinity. What do you go to? We go until negative 3. Beautiful. Okay then, we move on to the next interval. Interval's right here. Where does it start at? It starts at 2. What is it going to? Alright, so we have an arrow again. We have an arrow again right here. Now we have to be careful here. This arrow may be pointing down. Right, the arrow is pointing down. So this function value is shooting towards negative infinity. But the x value is moving this way. So the x value is positive infinity. Alright, so very careful right there. The x value is positive infinity. The y value, the function value, is negative infinity, but the x value, since you're moving to the right, is still positive infinity. So that is our decreasing interval. And lastly, constant. Alright, so this one does have a constant interval. It's right here. Yeah, so we're right here. Beautiful. That'll be 1. Oh, my bad. That'll be minus 3 to 1. Okay, so there you go. That is the constant interval. And going back to it, if you put parentheses here, I won't be upset. To me, it makes logical sense to include these values on the constant interval. We're going to move on from that discussion though. As long as you stay consistent, it does not matter. Beautiful. So those are intervals. Great. Now let's go ahead and talk about the relative max and mins. Alright, now we want to talk about the relative maximums. So, does this graph have any relative maximums? Right? It does. It has one right here. How do we know that? Well, this point, before the point, we are increasing up into the point. Immediately after the point, we are decreasing away from the point. So that is the behavior we're looking for. So this means 2, 4 is a relative maximum. How about relative minimums? Alright. Now this is where we have to be careful. Because do we have any relative minimums for these points, right? And we might think we do, right? Right here, let me use blue. Right here, that point, what is that? That's negative 3, negative 1. That point may look like a relative minimum, but we have to be careful. Because what is the behavior for a relative minimum? It is decreasing. Great. But what must come after the decrease? Immediately after the decrease, you have to be increasing. So we have decrease, we hit the point, and immediately after that point, we are constant. So we are not increasing right after the point. That does not satisfy the behavior of a relative minimum, so this graph has none. There are no relative minimums for this graph because we do not fully satisfy the behavior we're looking for. Okay, so that will be it for our how to read graphs portion. So now we're going to move on into this idea of translating graphs, and we're actually going to do some graphing. Let's get into this idea of translations of graphs. Okay, so translations of graphs. Before we get into that, this idea of translating graphs, I want to introduce something. I want to introduce this idea, I like to call it parent graphs. I think your book prefers to call them common graphs. Either way is fine. It's calling it, like I said, I prefer calling them parent graphs. What I mean by these parent graphs. So what we're about to learn is that graphing any function is really just a matter of graphing some variation of something we'll call a parent graph. So all paragraphs are these are the most basic types of graphs you can make for certain types of functions or certain types of equations. So the most basic of basic parent graphs is the constant graph, a function that never changes. And so all constant graphs look like, oh, I should probably do a different color. So all constant graphs just look like some horizontal line, all right? No matter what constant graph you draw, it will look like some horizontal line. Now, the next one we can move on from is the linear graph, or a fancy way of calling this is the identity graph. For those of you who know why it's called the identity, kudos to you. But, so, this is kind of the next step up. So this is a function that does not change. This is a function in which when you input something, it just pops out the input. So the input is the output. That is the most, that is the next basic paragraph we can construct. This is called a linear graph, right? So, not surprising, linear, line. That's exactly what the graph is. It is a line. So, in other words, all linear functions, all variations of this linear function will just be some variation of a line. That's all it means. So, these are our two most basic paragraphs: the constant function, flat line. Linear function, just another line but with a slope. Alright? So now let's move on to the next two types. So, take a little pause, copy. Okay, so next two types. So the next two we're going to talk about are, I believe they are, okay, so we have the absolute. I should have left the, we have the absolute value graph, so f of x equals absolute value of x. And then we have the square roots. We have the square root graph, so f of x equals square root of x. Okay, so what do these two graphs look like? Well, absolute value graph, I'm sure some of you know what it looks like. Just a V. So again, every single absolute value function, the graph of it will be some translation or some variation of that V. Square root graphs look like that. So all square root functions, when we graph them, they will be some variation of this graph. Alright, so those are the next two. Take a little pause, copy these. Alright, so we have two more I want to introduce. Two more I want to introduce. The last two I want to introduce are these. It is how do exactly they call it? So the squared, quadratic, there's a squared or quadratic function. So f of x equals x squared, and that looks like this. It is a u, right? For those of you who don't know, we call this a parabola. We call that shape a parabola. And the last one we're going to introduce is the cubed function. So f of x equals x cubed. That is our cubed function. And that graph looks like a curly S, like a snake. There you go. So those six. Those six are going to be some of the paragraphs that we're going to use. There's actually an infinite amount of parent graphs, as I'm sure you could probably all see that. So there are infinitely many parent graphs, but these six are going to be the ones we're concerned with, the ones we're going to use most often. What does that mean for you? I expect you to fully understand these paragraphs and then basically memorize them. So in other words, whenever I give you a quadratic function, I expect you to understand its graph will be in some way this u just may changed around. Whenever I give you a cubic function, I expect you to understand that it will be some form or some variation of this s. If I ever give you an absolute value function, it'll be some variation of the v, a linear function, some variation of the line. I expect you just to memorize these 6 connections that I just listed, okay? So these will be our parent graphs, and what we're about to understand, here's a very important note for the day. So take a moment, pause, copy this. Okay, so here's our important notes. Our important note for this is going to lead directly into this idea of translations. All functions. Oh no, let me start over. My bad. The graphs of all functions. The graphs of all functions are the graphs of all functions are just some unique or some okay, I'm going to start over. We're going to learn in cuts. Okay, so here's our important notes. Alright? It's going to lead directly into this idea of translations. And this note is this, that to graph any function, is just a matter of translating that function's parent graph. That function's parent graph. So in other words, if you can understand the parent graph of a function, you can understand how to graph any function that is a variation of that parent graph. That is a pretty powerful statement, and it's going to be a pretty powerful tool we're about to gain. So let's go ahead and get into that discussion at this point. Okay, so let's get into translations. Yeah, let's go. So when I introduced translations at the very beginning, I talked about how there's 2 big bodies, rigid and non-rigid. Alright? So let's dissect those a little more. Rigid breaks into these following cases. Vertical / horizontal shifts, reflections, reflections. Yeah, so it breaks into these cases, reflections and vertical / horizontal shifts. And then the other body, or the other type, is non-rigid. And non-rigid break down into just vertical stretches and shrinks. Alright, so we have 2 big bodies. The first body is rigid transformations, or rigid translations, and those are either vertical / horizontal shifts or reflections. And then we have non-rigid translations, and those are vertical stretches or vertical shrinks. Alright, so let's get into the rigid first. We'll start with the rigid. So rigid translations start first with horizontal. Let's actually start with vertical / horizontal shifts. So let's discuss these. Vertical / horizontal shifts. Alright? Yeah, that'll work. So first let's talk about vertical. So there are 2 types of vertical shifts. Oh, and actually, I guess I should. I'm about to introduce these types of shifts using abstract or generic notation. So we're going to let C be a real number, all right? Just to review notation, this is saying C is in, that means in, and this fancy R is real numbers, so C is a real number. That's what that means. Let C be a real number, and f of x be a function. Actually, you know what? Let's do this. F of x be a function. Okay? Alright, so we're going to let C be a real number, and f of x is our function. Now then, there's going to be two types of vertical translations. Okay? Well, let's think about this. Vertical, right? Vertical straight. Well, what are the directions you can move vertically? You can move up and you can move down. So that's exactly what we're going to describe. Our first one is a vertical shift up. So we're going to do a vertical shift C units up. C units up. Alright, I'm moving my graph C units up. What does that mean? How do you represent that? Wait, vertical translation is simply when you have your function and you add some value to it. This is you translating or pushing your graph up, is when you take your graph and you simply add a constant value to it, you push your graph up. That is a vertical shift up. So conversely, what is a vertical shift the other way, the other direction, down? So a vertical shift C units down. So this was C units up, and you added C. C units up, you added C. So I'm sure as we can all probably guess, if I want to move down, then h of x will equal f of x minus C. So you take away a value. You subtract away some constants. You move your graph down. So if I have my function, I subtract from it a constant, it will bring my graph down. It'll grab it and move it down. These are our first two types of translations, a vertical shift up and a vertical shift down. All right. We will do concrete examples in a bit. I just want to introduce these generically first. So take a moment, pause, copy. Beautiful. Let's go ahead and do now horizontal. So this was vertical. Let's now talk about horizontal. So a horizontal shift C units, horizontal shift C units. Right, so let's think about this. Talked about vertical, straight line, only way you can move is up and down. Now we're doing horizontal, flat line, only two directions, left and right. So a vertical shift C units right. Alright, let's think about that. What is a vertical shift, or my bad, what is a horizontal shift C units to the right? So first, let's think about this. Alright, so when I was talking about verticals, we took a constant and we added it to our function. Alright, why does that make sense? If I wanted to move my function up, I want to do a vertical shift up, I took some constant, I added it to my entire function. Let's think about that. Well, the function, whatever it outputs, that's a y value. All right. Remember, we're making points, and the output is the y. So if I add to my output, if I add to my function, I'm adding to my output. I am changing the y. I'm moving up and down. Now here, I want to move left and right. So what is the left and right value? Right. It's not the output. Left and right is our input. It's our x. X is left and right when we graph. X is our input. So if I want to be moving my graph to the right, do I want to be adding or subtracting to what? What do I want to be adding, subtracting to? Well, I want to be adding, subtracting to the x, because the x is my input. I want to be changing that input. So my C will be inside the function call. Now here's where we have to be careful. All right. What we have to be careful is that we want to move to the right. The right is the positive direction. So our gut instinct, intuitively, we think we should add C. Right? If I want to move to the right, I should be adding c to x. This is where you have to be careful. Horizontal translations are counterintuitive. It's the exact opposite of what we think should happen. We need to subtract c if I want to move to the right. Alright, so big idea here. Horizontal shifts are counterintuitive. Oh god, I probably spelled intuitive wrong. Whatever, you guys get the point. Horizontal shifts are counterintuitive. Never forget that. Big point. They are counterintuitive, alright? So if I want to move my function to the right, I need to be altering the x directly, but if I want to move to the right, counterintuitive, instead of adding, we will subtract. So that is a vertical shift, c units to the right. Now then, horizontal shift, the second version. If we're not moving right, we're going to move left. So here was right, here we've subtracted c. So now we're going to move the left. Now we're going to move left. And so what will our function be? So before we had h of x equals f of quantity x minus c, counterintuitive, right, subtract. Again, same idea holds, counterintuitive. We will add c. So to shift our graph, to push our entire graph to the left, we will add a constant value directly to x. That is a horizontal shift. Alright? So, here are our next two types of translations. Take a moment, pause, get these copied down. Beautiful. So, now let's talk about the next type of rigid transformations. And after I introduce the next type of rigid transformations, we'll go ahead and move into a concrete example. So, to start with, actually, you know what? I'm going to go ahead and erase this now. And before I get into the next type of transformations, let's go ahead and do two quick examples for these types of transformations. These horizontal and vertical. Let's do two quick examples. Alright, the two quick examples we'll do is this. So let's do an example. Let's do an example for our vertical shift up. Alright? So let's take f of x to be x squared. Let's take f of x to be x squared. So then, if I take h of x is x squared plus 2, alright, so this is 2 units up, right? We are moving our graph 2 units up. So let's go ahead and make a quick sketch. One second. 1, 2. Okay, so let's think about this real quick. Let's go over here and let's imagine our normal x squared graph. And it looks like that. Remember, going back to those parent graphs. And it has the points 0, 0. So what's going to happen now to our graph? We're going to graph h of x, which is just a vertical shift up by 2 units of our original parent graph x squared. So all we're doing is we're taking our graph and we're moving it 2 units up. So before, if I had my point 0, 0, right, I'm moving it up. I am changing the y value because y is vertical up and down. So before I had 0, 0, I'm moving that 2 units up. So I add 2 to the y and I now have the point 0, 2. Alright, that is my new point. And then simply the rest of the graph follows. Like I said, all we're doing is just moving that graph up. And so that is a vertical shift, 2 units up for our graph. We take our graph, the point 0, 0 becomes 0, 2, and the same exact shape is held. So that is an example of a vertical shift 2 units up. Let's do an example of a horizontal shift now. So I'm going to go ahead and erase this paragraph, but make sure you keep that in the back of your mind. So let's do an example of 4. And so 4 for us was moving c units to the left. Alright? So again, that'll be our parent function, f of x equals x squared. Let's go ahead and create the graph. H of x equals... Now, so let's do 2 units to the left. Let's do 2 units left. Alright, so everyone take a moment, pause now, and try to figure out what will h of x look like. So for 2 units up, this was h of x, x squared plus x. We added a constant 2 to our function x squared. For horizontal shifts, remember we need to add and subtract directly to the x. So what will h of x look like? Take a moment, pause, see if you can figure that out. Okay, so what will this h of x look like? Remember, we are adding or subtracting directly to the x. We are moving left. Left is the counterintuitive, right? Remember, horizontals are the counterintuitive. So if I'm moving left, I'm not subtracting, I am adding. I am adding, and I'm adding directly to x. That is why h of x looks like this. We add 2 to x inside the function. Our function was x squared, so it is now x plus 2 quantities squared. That will successfully shift us 2 units left. What do I mean by that? Well, here's our quick sketch. Remember, before we had the point 0, 0. Okay? We were doing a horizontal shift. Horizontal is the x-axis. We are changing the x. I am taking away 2 from the x. I am moving 2 units left. I am taking x and I am hopping it 2 units over to the left. So 1, 2, I'm now at negative 2. I have the points negative 2, comma 0. I shifted 2 units left. The x went to the left direction by 2 units. And the same shape is still held. So there's an example of a horizontal shift left. Okay? Beautiful. Now let's go ahead and get into the other type of rigid transformations, which are our reflections. Let's talk about the reflections now. So pause, take a moment to copy this. All right. So, next type of transformations for rigid is reflections. Okay? Now, there are 2 types of reflections. And we mean reflecting across axes. So, our first type, we'll go and say, is reflection across the x-axis. Alright, we're going to do reflection across the x-axis. Alright? So, what is that? How do you successfully reflect across the x-axis? Again, let f of x be a function. Again, we're going to let f of x be some function for our generic notation. So, what will a reflection across the x-axis look like? Alright? What it means to reflect across the x-axis algebraically is it means you want to negate your function. You want to negate the function. What does it mean to negate the function? Simply multiply it by a negative 1. So negative f of x will be a reflection across the x-axis. How does that look visually? Let's go and do an example. So we'll use f of x equals square root of x. Okay? So f of x equals square root of x. Just to recap, quick recap. Alright? That is the parent graph. It has the point 1, 1 on the parent graph. I now want to reflect this. Okay? So, what will that function look like? What will my h of x be? So, we simply go back to this definition. A reflection across the x-axis simply means you want to negate your entire function. Multiply your entire function by a negative. So my function is square root of x. I want to multiply that by a negative number. Hence, h of x is minus square root of x. Okay? How does that look visually? How does that look visually? Well, just think about this. Up here in this parent graph, I input 1, and I output 1. Square root of 1 will equal 1, so when I input 1, I output 1. Okay? What's going to happen here? I'm going to input 1. Let's say we input 1. What will I output? So before I outputted just positive 1. Now I'm going to be multiplying that by a negative number. So when I input 1, I output negative 1. Alright? If you have trouble seeing that, take a moment, think about it. Try to convince yourself that yes, when I input 1 into h of x, I will output negative 1. Okay? Another example of a point right here on the graph is the origin, 0, 0. So let's try that. When I input 0 into this, what am I going to get? Right? We're still going to get 0. Again, if you have trouble seeing that, take a moment, pause the video, try to convince yourself. So when I input 0, I'm still going to output 0. When I input 1, I'm going to output minus 1. And so, we're going to create a shape like that. Okay? That will be the reflection across the x-axis of that graph. So in other words, what we can see visually is that to reflect across the x-axis, visually, all it means is fold across. Oh, I spelled across wrong. Brain farts. Alright, so we just fold across the x-axis. Right? When you're doing a reflection across the x, all you do is you take that original shape and we just fold it over. You just fold it over across the x-axis. And that is how visually you construct a reflection across the x-axis. So let's go ahead and do now a reflection across the y-axis. That'll be our second type of reflection. So take a moment, pause, and get this all written down if you haven't done so already. Okay, so let's go ahead and do a reflection across the y-axis. Reflection across the y-axis. What will that look like? What will h of x be? So let's go ahead and take a moment and let's think about this. So what happened when we had verticals? When we did vertical shifts, we added or subtracted a constant outside the function. Okay? Then, when we did horizontals, the difference was when we did horizontals, we added or subtracted a constant directly to x. So in verticals, we added or subtracted outside the function. For horizontals, we added or subtracted directly to x. Alright? And that pairing, right? We see a lot, that happens a lot in math, where there's these pairing between things, alright? So verticals was outside the function, horizontals was inside the function. The same exact idea holds for reflections. For a reflection on the x, we multiplied a negative outside the function. So reflection on the y, where do you think we're going to multiply the negative? Alright, so take a moment, pause, think about it, and see if you can come up with an h of x. Go ahead and do so now. Alright, so, yes, the pairing between reflection across the x and reflection across the y is directly similar to the pairing of vertical and horizontal shifts. Just like vertical shifts, reflection across the x-axis affects outside the function, and just like horizontal shifts, reflection across the y will directly affect the x. In other words, f of minus x is our reflection across the x-axis. So to reflect across the x-axis, you negate the x. Oh, my bad. I think I said that wrong. Reflection across the y-axis, you negate the x. And reflection across the x-axis, we negated the function. For reflection across the y, you negate the x. For x-axis reflection, you negate the whole entire function. Okay, so there you go. All right, so going back to it, let's do this example right here. Let's use the same parent function, square root of x, but what will h of x equal? All right, so just think about it. We're following with the definition. We are doing f of negative x. So if my f of x was square root of x, I want to do f of negative x. In other words, I want to plug in minus x wherever I see an x. So h of x is square root of minus x. This will create a reflection across the y-axis. All right, a reflection across the y-axis. So what will that shape look like? What will that graph be? Well, let's think about it. What did we do in a reflection across the x-axis? In x-axis reflection, we took our original shape and we folded it over the x-axis. So now we're doing y-axis reflection. So, unsurprisingly, what does that mean for us? We will fold the graph over the y-axis. Alright, so to do a y-axis reflection, you take your parent graph and you just fold it over the y-axis. For x-axis reflection, we folded it over the x-axis. For y-axis reflection, we will fold over the y-axis. So if this was my original image, I now create is that one. Alright, and hopefully we can all see the point 1, 1 will now become the point negative 1, comma 1. And there you go. We've reflected across the y-axis. Beautiful. So, those are types of rigid transformations. Okay. We have horizontal and vertical shifts, and we have reflections across the axes. So, if you don't have this written down, take a moment, pause the video, and write all this down. Okay, so now before we move on, I want to make some points, some comments about reflections. Okay, so I want to make some comments about reflections. And arguably this will be our most important note, our most important star for the day. And what we're about to do immediately after this is we're going to get into an example. We're going to do an example that has multiple types of translations going on at one time. Alright? And so what's important about this, what's important to remember is as we do this example, is that when dealing with functions containing multiple translations. So when you have multiple translations, always do reflections first. Always do reflections first. Okay? Most important notes. This is the example we're about to do, and any problems moving forward, if they have multiple translations, always do your reflections first. Handle those first before anything else. If you don't handle those first, there is something very weird and just doesn't make sense you have to do later on. So we're just going to totally ignore it. We're not even going to bring it up, and we're just going to remember that for any problem that has multiple translations, reflections are done first. Beautiful. So, take a moment, make sure you get that written down. This is an important note. Always, always, always do our reflections first. So, pause, write this down. Great. Now, let's go ahead and do a bigger example that kind of brings in these multiple translations into one example. Okay, here will be the example. So let's describe the translations in words. Let's describe the translations in words, then create a sketch. Okay, we're going to describe the translations in words, then create a sketch. So I'm going to go ahead and erase these directions because I'm going to need as much space as I possibly can get. So please, write these directions down right now. Pause the video, write this. Okay, so I'm going to go ahead and erase this now. Just understand these are the directions for this example. So what is the function we're going to look at? The function we're going to look at is this. H of x equals minus x plus 3 cubed plus 2. Okay? Here is the equation we're going to be concerned with. So we want to identify the translations happening on this function, then we want to create a sketch. Okay? So before we do that, before we even start talking about the translations, let's first figure out instead, what is my parent function right here, right? So as I said, what is an important note from today's class? When graphing any function, it is just a matter of graphing some version of a parent graph. So what we have to start getting comfortable with is identifying what are our parent graphs. So what is the parent graph here? All right, what is our parent graph, our parent function? What is it? And hopefully you'll be able to see. If not, don't worry, we'll get practice with this. We'll start gaining this tool in our heads. But let's think about this. What generates our translations? Things that generate our translations are when we add or subtract constant values or when we multiply by negative numbers. These are what make our rigid transformations. So this adding 2 will be a transformation. This adding 3 will be a transformation. This multiplying by a negative number will be a transformation. So when you're trying to identify the parent function, simply ignore all the things that make translations, that do some rigid transformation or non-rigid, as we'll get to in a second. But ignore those and look at what's left over. What is the defining feature of your equation, of your function, after you ignore all those other things? And for us, our defining feature is that cubed right there. And so that is why f of x equals x cubed is the parent function for this example. All right? So after we identify that, let's go ahead and list our transformations now. Or translations. Let's go ahead and list those. All right? And I've already listed them off, right? So let's go ahead and just make sure we understand what each one is. So this plus 2, that is a translation, right? Well, what type of translation is it? Well, we understand now that our parent function is x cubed. Where is this plus 2 happening? It is happening outside of the cubed. In other words, I am adding to the function. That right there is an example of our vertical translation. So for us, if I'm adding 2, this is a vertical shift 2 units up. So one of them is a vertical shift 2 units up. Beautiful. There's one translation identified. What is another one? Well, we have another addition going on. Let's go ahead and talk about that. So where is this addition happening? Where is it happening? Well, I am directly adding to the x value. I am adding inside that cubed. All right? So I'm directly affecting x. This is an example of a horizontal translation. Horizontal shift, we're doing 3 units. And remember, horizontals are counterintuitive. I am adding 3, so that does not mean I'm moving to the right. Counterintuitive, I'm adding 3, we are moving 3 units left. 3 3 units left. Beautiful. Now, there is one more translation present. I've used up my covers, so I'm going to go back to black. Alright, and that is the multiplication of the negative. That is our last translation. And again, we have to ask ourselves, where are we multiplying this negative number? Am I multiplying outside the parent function, or am I multiplying inside the parent function? And we can see here I am multiplying outside the cubed, so this for us is a reflection across the x-axis. We are reflecting across the x-axis. There you go. So we have identified all 3 of our translations present in this example. Here they are. So take a moment now, pause the video, understand for yourself why this is the case if you're a bit shaky on it, and then make sure you get all this written down, because again I'm going to erase all of this and we're going to start from a fresh board. So take a moment, pause now, and make sure you're caught up with me up until now. Okay, so we've just done half the problem. We've identified the translations. Let's now create our sketch. And for the time being, I want us to do our sketches like this. I want us to go through the process of creating each individual sketch, applying each translation individually. What do I mean by that? So first we're going to start, I guess before we do anything, as you saw when I was doing my first couple examples introducing these ideas of translations, I always kept track of one point. Like when we did the x squared, I kept track of 0, 0 and how it changed. When we did the square root of x, I kept track of the point 1, 1 and how it changed. I want you guys to do that the same thing here. So always keep track of 1 point and how it changes. For the time being, I want everyone to make sure they do this in homework assignments and exams and stuff like this. Always keep track of at least 1 point and how it changes under your translations. So, let's go ahead and do that. And yet again, I want as much space as I possibly can because I'm about to do quite a few sketches. So I'm about to erase this, pause the video, get this written down. For your homework and exams, I want you to be doing this. Alright, so let's start with the parent. So our parent function was x cubed. So our parent function looks something like that, and we have the point 1, 1. Okay, so now I want to create the final sketch of h of x, our original function. But as we do that, I want to go through the process of applying each individual translation. Alright, so which one should we do first? We had 3 to work with. We had the vertical shift, the horizontal shift, and the x-axis reflection. So what do we do first? And this goes back to that note. Hopefully you all wrote it down. We always do our reflections first. So that's the first one we're going to start with, is we'll reflect on x-axis. We will reflect on the x-axis first. Alright? So what does that become? Remember, all we do is we take our image and we fold it over the x-axis. So we now get this. That is the shape we get. Alright, and as I said with that other note, I want you to keep track of at least 1 point. So what does 1, 1 become? Well, it's going to become -1, 1. My bad. 1, -1. I said that in the wrong order. It'll become the point 1, -1. Beautiful. So there's our first reflection, our first translation done. Let's do the next one. And at this point, it doesn't matter what we do. We did the reflection first. That's all we had to make sure of doing. At this point, you can do whatever other translation you want in any order. So let's do the vertical shift one. So vertical shift 2 up. All right, we're going to do a vertical shift 2 units up. going to do a vertical shift 2 units up now. So the points 1 comma negative 1 will now become the points. I wanted 2 up. I'm going to add 2 to the y value. So it's going to become 1 comma 1. Yeah. It'll become 1 comma 1. But we need to be careful. So let's actually go back and let's keep track of another points. Here I had the point 0, 0. Here I'll still have the point 0, 0, right? But I will no longer have the point 0, 0 here, because that point 0, 0 will become, adding 2 to it, the 2 to the y value will become the point 0, comma 2. And that is why my graph from this point looks something like this. There you go. Okay, now lastly, we have one more left. Let's go ahead and do our horizontal shift, and we were horizontal shift 3 left. Lastly, let's do our horizontal shift 3 units left. Again, I am changing the x value. So if I had 1 comma 1 before, I'm moving to the left. I am taking away 3 from that x value. I'm going to get the points negative 2 comma 1. Alright, conversely the point 0 comma 2, I'm going to move 3 to the left. I'm going to change the x value. That point becomes negative 3 comma 2. And so I get some shape like that. And this right here is our final sketch and the second portion of our final answer. There you go. Alright, so take a moment now, pause the video. This right here is pretty much what I would like to see on homework and exams, at least for the time being. When you get to like calculus and stuff like that, you won't need to do stuff like this for now. But for now, just to make sure we're understanding the material, do me a favor and do these individual translations and stuff like this. Okay, so there was an example. Beautiful. Okay, so now we're going to do another type of example. But this time we're gonna reverse the script a bit. So for this example that we just did, we wanted to give it a function, identify the translations, and then create a sketch. So now we're going to do the exact opposite, or not the exact opposite, but close enough to the opposite. This time, for this example, I'm going to give a graph, and then we want to identify the translations and identify the function that makes this graph. So, identify the translations and create the corresponding enough room. Okay, so in this example, I'm going to give a graph. Then we're going to look at the graph, we're going to identify the translations that's happened to this graph, then we're going to go ahead and create the function that makes that graph. So again, I'm going to erase the directions because I'm going to need the board space. Take a moment, pause the video now, make sure you get these directions written down. Okay, so now let's go ahead and do this example. So here will be the graph we're concerned with. Alright. I can make that better. There you go. Okay, so here's our graph. Okay? So, we want to identify the translations that have happened to this graph. And as always, before we even talk about translations, let's first identify what even is my parent function. Is the parent function. Alright, how do I identify that? How do I identify the parent function? Well, just like when we were given the function, how do we identify the parent function given a function? We ignored all the adding, subtracting constants, we ignored all the multiplying by a negative number, and we just said, what is the bare essence of what's happening here? So in our previous example, we saw that the bare essence was we were cubing something. Alright, so conversely, when I give you the graph and you want to identify the parent function, ignore all the directions it's pointing, ignore where it starts, if it's like floating here, over here, if it's like up here, maybe down here, ignore all that. All you want to do is just identify the basic shape. The basic shape. Identify the basic shape. And for me, I can see that my basic shape is just that. That's what the basic shape of this graph is going to be. And so all you need to do is go back to our list of parent graphs, or eventually have that list memorized in your head and be like, well, what function has that basic shape? This corresponds to f of x equals square root of x. So I already know, starting this problem, I am talking about a square root function. Beautiful. That is how we would identify the parent graph for this example. So again, I'm going to need the board space. Take a moment, pause the video, get this blue portion written down. I'm going to erase it. So go ahead and pause now. Alright, so that is our parent function. Our parent is square root of x. Let's now identify the translations that are going on. Okay, and we have to go back, and how do we do this, right? So again, go back and remember, right? So here we can see is the start of our graph. So we recall, square root of x starts at 0, 0. It started at that point 0, 0, right? If you can't remember that, go back and look at our sketch. It started at the point 0, 0. So ask yourself, how does the point 0, 0 change? Because right here, we have the points 3, negative 1. So how does it, and this is where it starts. So how did 0, 0 change into 3, negative 1? Okay? Well, we'll get to that. But as always, before we even get to that, we need to, oh, I just noticed I spelled recall wrong. So before we even get to that, what is something else we need to remember, right? I forgot it myself. Before we do anything, before we even talk about horizontal and vertical shifts, we need to understand, did we reflect? And yes, we can already see that we did reflect our points. We did reflect this graph. We reflected in which direction? Take a moment now, pause the video, see if you can identify for yourself. There was a reflection that happened here. Which axis did we reflect across? Pause. Okay, so we reflected across the y-axis. Alright, how can we see that? Our original shape was this, but we're now pointing in the other direction. We folded across the y-axis, so we're going to have a reflection across the y-axis. We have a reflection across the y-axis. There you go. We've identified one for reflection. Right? Again, how do we see that? We understand the parent function points like this. We are pointing this way. We grab this, we folded it over. In other words, we were folded across the y-axis. We have a reflection across the y-axis. Okay, so with that out of the way, let's get back to those translations. I have the point 3, negative 1. How did this graph, how did this point 0, 0 change into the point 3, negative 1? Well, let's look at the y. I went from 0y to a negative 1y. I moved down by negative 1. So I have a vertical shift of 1 unit down. Alright, let me go ahead and color coordinate. we had a vertical shift 1 unit down. Alright? So, next is that x value. It was 0 before, it's 3 now. So I'm going to have a horizontal shift 3 units. Now remember, is this going to be right or left? Well, this time it's easier for us to identify. We can see that we've moved right. Counterintuitive of I'm moving right. So we're moving right. Oh, okay, my bad. Just for now, keep in back of your mind that counterintuitive stuff. We're about to get to in a second. But this one, it's easy to see that we moved 3 units right. Alright? So, here are our 3 translations. We have reflection across the y, we have a vertical shift 1 unit down, and we have a horizontal shift 3 units right. So, let's try to create the function that encompasses all of these translations. So what is my h of x? So I know the core of it will be the square root. Alright? Now, is there anything I want to add or subtract outside my function? Let's start there. And yes, right, we do have a vertical shift. We have a vertical shift 1 unit down. So I know I'm going to be subtracting outside my function. So, and let's leave all this open space. We're going to be subtracting 1 outside the function. Now, I also have a horizontal shift. I have 3 units right. And remember, that is directly affecting the variable x. Horizontals directly affect the x. So I have my x, I have my 3. I want to affect the x directly, so I put it inside the square roots. And this is going back to, remember, counterintuitive. We are moving right, counterintuitive. I don't add, I subtract. So I have x minus 3. Lastly, let's go ahead and check them off as we use them. Lastly, we need to account for the reflection. I have reflection across the y-axis. So where do I negate? Because remember, reflections are all about negating something. Which one am I negating? The function or the x? That's where we go back and we say, yes, when I'm reflecting across the y-axis, I need to negate the variable x. In other words, I need to put a negative right there. And so that is my function h of x. This function right here will create this graph. That is what we have just shown. Okay, so that is that example. Beautiful. Okay, so we've finished up with rigid transformations at this point. We did 2 big examples for them. Now I'm going to go ahead and briefly go through the other body of transformations I talked about, I mentioned at the very least, these non-rigid transformations. Alright, and there's going to be 2 big types. They can be broken down into vertical stretches and shrinks. Now, I'm not a big fan of these transformations or translations. I think the rigid ones are much more interesting and much more fun to use. These ones, they're kind of bland. I'm just going to briefly mention them, so just so you know about them, but not going to worry about them too much. Alright, so we have 2 types. We have a vertical stretch. Okay, so how do we represent this? Right, for us, a vertical stretch is when h of x equals c times f of x. So when you're multiplying your function by a constant, alright, and what's going to be the main portion of this, what actually makes this a vertical stretch, the important fact is that this constant, we're going to make the claim, this constant is bigger than 1. Alright, so this is the big idea. You have a vertical stretch when you're multiplying your function by a constant, and the key feature is that this constant is bigger than 1. This is what makes a vertical stretch. Analogously, a vertical shrink is the same, starts the same way. It's h of x will equal c times f of x, so our function multiplied by a constant. But here where the important feature was the constant was bigger than 1, it's going to be the opposite. And it's our constant is between 1 and 0. So when your constant is between 1 and 0, that is an example of that is what we classify as a vertical shrink. So both of these vertical shrink and stretches are the results of multiplying our function by a constant value c, but the difference between them is that you get a stretch when the constant is bigger than 1, and you get a shrink when the constant is between 1 and 0. So these are the last two types of transformations, and we'll do 2 quick examples just to end today's video. So here are the examples. Here will be the examples, all right? We'll do a vertical stretch first, and we'll use f of x equals absolute value of x, okay? So as we know, we use that as our parent function, so to give a quick sketch, to give a quick sketch, we get that V shape, and it has the point 1, 1. Point 1, 1 will be on our graph. So, if we want to do a vertical stretch, for example, a good example of that is 3 times absolute value of x. This will be the example of a vertical stretch. Why is that? We have our parent function, absolute value of x. What are we doing to it? We are multiplying by a constant value 3, and 3 is bigger than 1. So this is an example of a vertical stretch. So, to help emphasize, 1, 2. So these are kind of hard to visualize. They're both easy and hard to see visually, in my opinion. The reason why, I guess this one will be a good example. Never mind. Right. Okay, so there we go. So this is how our graph will look, and if you try at least to compare it to the original graph, hopefully you can kind of see this idea of stretching it. We've taken our original image and we've kind of just pulled on it, and we've made a thinner stretched image. So stretched the original graph, stretch the function. That's the kind of visual argument, is that we're grabbing this function, we're kind of pulling on it, we're stretching it. Okay, so then a quick example of a squish, or a shrink, my bad, is that. We'll go ahead and say 1/3 times absolute value of x. Again, how do we know this is a shrink? We have our parent function, absolute value of x. What are we doing to it? We are multiplying by a constant value. What's important is that constant value is less than 1 and bigger than 0. So this is an example of a shrink. Okay? So, plotting this real quick, that point 1, 1 will become the point 1/3. 1, 1/3. So we get something like this. And this one, I guess, is 1, 3. So yes, now we have this point 1, 1/3, and yeah, they use the word shrink. I think shrink is not a good way to describe this. I think a better, more intuitive way to describe this is that we're squishing it. Right? We've taken our original image, we've pressed down on it, we've squished it out. So we've taken that V, we've spread the V apart, we've squished it down. That's kind of the visual argument for this example. Squished the function. And there you go. That's all non-rigid transformations are. They are either this idea of stretching your function out or smashing it down. Like I said, they're not very complicated. In my opinion, the rigid transformations or translations are much more interesting and much more fun. But there you go. Those are the last pair of translations, and that'll be it for our first test video for the semester. Like I said, this will probably be how we are moving forward for the rest of the semester, at least until hopefully we come back to in-class lectures, but that remains to be seen. Regardless, here it is. Please give me any feedback through email, Canvas, YouTube comments, whatever is your preference. But please, feedback would be greatly appreciated. Hope everyone has a wonderful day.